Welcome viewers to the seventh lecture for the online series of lectures for the course of differential geometry. We are going to discuss submanifolds in this lecture, various aspects of submanifolds. So let me get started with some definitions. A subset S of a given manifold n of dimension n is a regular submanifold. By submanifold, we will mean a regular submanifold of dimension k if for every point P in the subset S there is a coordinate neighborhood u comma phi, which in terms of local coordinates we can write as u comma x1 x2 all the way up to xn of P lying in the maximal atlas of n such that U intersected with S, this subset is defined by the vanishing of n minus k coordinate functions on it. N minus k coordinate functions. Now, by renumbering the coordinates, their n coordinates and n minus k coordinate functions vanish, and we can renumber the coordinates in such a way that the last n minus k coordinates vanish, okay, so that the first k coordinates are non-vanishing. We may assume that these vanishing n minus k coordinate functions are xk plus 1, xk plus 2, all the way up to xn. So we immediately see that there are xn minus k such coordinate functions, right? Good. We call such a chart u comma phi in an adapted chart relative to the subset S. On this intersected subset, phi is given by this n tuple of coordinate functions whose first k coordinates are x1, x2 all the way up to xk, and the last n minus k coordinate functions vanish identically, right? Now let phi s from the subset u intersected with S to R to the k be the restriction of the first k components of phi, first k components of phi to the subset U intersected with S. That is a subset of U. Remember, phi is a map from U to R to the N. Okay. Now, phi sub S is the restriction of this map phi to this subset. That is, now phi S will be just a k-tuple, x1, x2, all the way up to xk. Now, note that this pair U intersected with S comma phi sub S is a chart for S in the subspace topology. So S is a subset of the given manifold, and we equip S with the subspace topology, and then S is a topological space, and it's easy to check that this pair is going to be a chart for this topological space S, equipped with the subspace topology that it inherits from the original manifold N. Okay. Now, the definition of codimension. If S is a, remember that if S is a regular submanifold of the given manifold N, then for each point P of S, we'll be able to find an adapted chart of, for each point P of S, we can find an adapted chart of the manifold N relative to S. Okay. Now, if S is a regular submanifold of dimension k, right? So we can find n minus k vanishing coordinate functions if k is the dimension of S, right? Of dimension k in a manifold n of dimension n, then n minus k is said to be the codimension of S in N. Okay. Good. Now a remark to this definition. Remark to the definition of regular submanifold. As a topological space, a regular submanifold of N is required to have subspace topology. Okay. It's also noteworthy that dimension k of the regular submanifold S may be equal to the dimension n of the original manifold of the manifold n, in which case U intersected with S is defined by vanishing of no coordinates, is defined by the vanishing of none of the coordinate functions, none of the coordinate functions, right? So that n minus k is equal to 0. So that, in other words, phi restricted to U intersected with S, which we defined as phi sub S, remember? And that is nothing but phi in this case. Therefore, an open subset of a manifold is a regular submanifold of the same dimension. Right? Since n minus k is equal to 0, n is equal to k. Okay, the dimension of the regular submanifold is the same as the dimension of the original manifold. Okay, now it's time to give you an example of a regular submanifold. Example 1. The interval, okay, but before I go over the first example, I need to mention an important, a subtle aspect of the definition of an adapted chart relative to the submanifold. It's important, note, it's important to note that U intersected with S is supposed to be the maximal region of U. Region of U where n minus k coordinate functions vanish. Coordinate functions vanish for U to be called an adapted chart. An adapted chart relative to S. Okay, so suppose this is the open subset that I have in the manifold N. Okay, this is the manifold N, and this is the open subset U, and this is the regular submanifold S. Okay, and these bold part of the subset S is U intersected with S. Okay, so uh, when we are calling U an adapted chart relative to this regular submanifold S, we are ensuring that the n minus k coordinate functions vanish identically on U intersected with S. By that we mean that this is the maximal region of U on which these n minus k coordinate functions vanish, meaning that on no other points of U except for U intersected with S this happens, right? If I pick up a point here which is outside U intersected with S, there I will never have the n minus k coordinate functions vanishing identically. Okay, this is the maximal region. So in any of its subset, of course these n minus k coordinate functions vanish, right? But this is the maximal region that we can get, on which maximal region of U on which these n minus k coordinate functions vanish. Okay, so this fact can be written like this. The inverse image of phi, the inverse image of this subset under phi. Okay, how do I write? So the elements of which look like this. So these are by star we mean some unknown coordinates, right? They can be anything, and there are n minus k many zeros here, zeros here. So these are elements of R to the n. Okay, such that these stars are unknowns. So if I take this set and take the inverse image of this guy, this set under phi, that is going to be U intersected with S. Okay. So I take all such elements and they constitute a set in R to the n, and take the inverse image of that set under phi, and that is going to be U intersected with S. Okay, so now it's time to go over an example. Let me erase everything. Example 1. The interval S defined as the open set from -1 to +1 on the x-axis is a regular submanifold of the xy plane. Okay. Now, as an adapted chart for any point here, any point P in S, we can choose the open square U minus 1 comma 1, Cartesian product minus 1 comma 1 with coordinates x comma y of the plane R2. Then one immediately finds that U intersected with S is precisely the zero set of Y on U. By the zero set of Y on U, we mean the set on which Y vanishes. Okay, so let me draw a picture for this. This is the y-axis, and this is the x-axis, and this is minus 1, this is plus 1. Okay. Now I am taking the open square. This is plus 1, this is minus 1. So this is the open square. Okay. And this is an adapted chart. So check that this open subset minus 1 to plus 1. These so this is actually U intersected with S, right? This is nothing but minus 1 to plus 1. And this is the maximal region on which this y coordinate vanishes identically, right? So if I pick up any other point on U, this is U, this open square. If I pick up any other point on U, except for this this subset U intersected with S, then the y coordinate will not vanish on those points. Okay, only if I only pick up a point from U intersected with S, then on that point this y coordinate will vanish. Okay, now I give you an example for this particular case, which will not be an adapted chart. Okay, so I need some room. On the other hand, if V is this open square minus 2 to 0 cross minus 1 comma 1, then V comma x comma y, x comma y are the x and y are the usual coordinate functions on the two-dimensional plane R2, then this guy is not an adapted chart for any point P in this subset, which is nothing but the intersection of this open square with the subset S, which is, what is S? S is this subset of the real line minus 1 comma 1. Okay, so let me draw a picture for this. This is the x-axis, this is the y-axis, this is 0, and this is -1, and I pick up this point, which is -2. Now I have to find the square. -2 to 0, and Cartesian product -1, 1. Okay, so this is the open square that we are looking at, which we denote by V, right? This is +1, this is -1. So this is V. And let me draw S here. This is this subset of the real line is S. Okay, so okay, and now this is not, now the point is that this open square V is not an adapted chart. Okay, why? This is because the zero set of y. By the zero set of y, we mean the set on which the y coordinate vanishes. The zero set of y on V, okay, is -2, 0, right? Is this whole set here on which this y coordinate vanish identically. Okay, see that if I pick up any other point from this open square V, the y coordinate will not vanish identically. Only on this set, this is the maximal set on which this y coordinate vanish identically, and this is not equal to V intersected with S, right? Because V intersected with S, this open square intersection, this open set S is going to be just -1, 0. -1, 0. Right? So V intersected with S is not the maximal region of V on which this is not the maximal region of V on which this y coordinate vanish. There are other points here. Okay, the other points here on which the y coordinates vanish. So that is why this is not an adapted chart. Now, with referring to this particular example, I give you another instance where we can find an adapted chart. Okay, so one instance is already discussed where this is -1, this is +1. Okay, and we have seen that this can be an adapted chart, right? So where we denote this point to be +1 and this point to be -1. Okay, so we have seen that when we take u to be equal to -1 comma 1, Cartesian product -1 comma 1, we immediately see that this open square u is an adapted chart uh, for the manifold for, relative to the square, relative to the open set -1 +1, right? But we can also take, so instead of taking this open square, if I choose the open square to be something like this, this is -1, this is +1, and this is, say, 1/2, 1/2, and this is again same as before, +1, -1. Now if I take this open square, instead of this open square, okay, this is an adapted chart. So -1/2, sorry, -1 to -1 to so -1/2 to +1/2 cross -1 to 1 is an adapted chart for any point P in -1/2 to 1/2, which is a subset of -1 to +1, relative to the regular submanifold S -1 to +1. Why? Because if I, so this is my new u, okay, this is the u. So what is u intersected with S? Tell me. So u is this square, and if I take the intersection of this guy with -1 to 1, this open set of R, then we see that the intersection is this subset, right? And that is the maximal region of this open square on which the y coordinate vanishes identically. Y coordinate vanishes identically. So we are good with the condition of adapted chart, and hence this is an adapted chart for any point P from -1 to 1/2, right? If I choose any point here, for that point, this open square will be an adapted chart relative to the submanifold S equal to -1 to 1. All right. So This was one example of adapted chart. This is another example of an adapted chart relative to any point here for this particular example. Okay, now I leave an exercise for you at this point, which relates to the topology sine curve. Show that the following subset of the two-dimensional plane R2 is not a regular submanifold of R square. Let gamma be the graph of the function f of x is equal to sine 1 over x, okay, on this interval 0 to 1, and let I be the open interval on the y-axis. Okay, I I is the set of all such ordered pairs 0 comma y in R2 such that y lies between -1 and +1. Okay, and then I define gamma I define S to be equal to gamma. Gamma is the graph of the function f of x equal to sine 1 over x on 0 comma 1, and I take S to be the union of these two sets, S, gamma, and I. I is this set. Okay, you need to show that S is not a regular submanifold. So you have to show that there exist points on this set around which you won't be able to find an adapted chart. Okay, all right, so this is the exercise. Now the first proposition of today's lecture, well, for the definition of regular submanifold, we just gave the definition, but we never proved that regular submanifold is actually a manifold. These proposition will prove that the way we defined a regular submanifold is actually a manifold. I mean that we will be able to find an atlas for the regular submanifold through this proposition. Proposition 1, let S be a regular submanifold of a given manifold N, and calligraphic U is a collection of pairs U comma phi be a collection of compatible adapted charts of the manifold N that covers S. Okay, so the definition guarantees that we can find such adapted charts around each point, right? Now those charts are actually the charts of the original manifold N. And since um, N is a differentiable manifold, these charts are compatible with C infinity compatible with each other, right? So the proposition tells us that that these pair that we can form out of this collection, these collection of pairs that we can form out of this collection, U intersected with S, comma, phi sub S. We already defined what phi sub S is. It's the restriction to of this homeomorphism phi to the subset U intersected with S. This collection is an atlas for the regular submanifold S, so that it has a differentiable structure. Therefore, a regular submanifold is itself a manifold. If n has dimension small n, big N has dimension small n, and big S is locally defined by the vanishing of n minus k coordinate functions then dimension of S is equal to k. Okay, so let us prove it. Let me draw a picture for you here. So suppose okay, I think I need some I have to fix the charts. Let U comma phi, which in terms of local coordinates should read U comma x1 comma x2 all the way up to xn, and V comma psi is V comma y1 comma y2 all the way up to yn, be two adapted charts in the given collection calligraphic U is equal to the set of all such pairs, right? U comma phi. So ideally we should have attached an index here, U alpha, phi alpha, and alpha should vary in an index set, and we form a set of we form a collection of all such pairs, U alpha, phi alpha, and that is going to be this collection. But now, for simplicity, we are not introducing that index here for notational clarity. Okay, but we can attach the index here to be more precise, but let's not do it for notational clarity. We assume that these two charts intersect, because if they don't intersect, then the result will be can be proved vacuously, then the result will be vacuously true. um, so we assume that they intersect, so that we are dealing with the non-trivial situation. Okay, so now let me draw the picture. U and V are the two open sets that intersect, and S is the regular submanifold. This is S. Now this is the chart, this is the homeomorphism phi for the chart U comma phi, and this is the map of the image of U under phi. Okay, this bold line is the image of phi, sorry, image of U under phi, phi of U, sorry, not that one. So this rectangle is phi of U, and this bold line is phi of U intersected with S. It's the image of this part, U intersected with S. So let me draw, denote it here in the picture, U intersected with S, and this part is V intersected with S. This is psi of V, and this bold line is psi of V intersected with S. Okay, and this is the homeomorphism psi. So let me name the figure overlapping adapted charts relative to a regular submanifold S. Okay, all right. Now from the definition of adapted chart, which we provided in the beginning of this segment, adapted chart relative to the regular submanifold S, relative to the submanifold S, it is possible to renumber the coordinate, number the coordinates such that the last n minus k coordinate functions vanish. N minus k coordinate functions vanish on points uh, on points on S with the open set of the pertaining adapted chart, right? For example, U and V. Therefore, for P in U intersected with V intersected with S, phi of P is equal to x1, x2 all the way up to xk, and the remaining coordinates vanish. And psi of P is equal to y1, y2 all the way up to yk, and the remaining coordinates vanish as well. So that the restriction phi sub s of P is going to be just the first k non-vanishing components, and for the other chart, phi sub s of P is equal to y1, y2 all the way up to yk. Therefore, we find that psi s composed with phi s inverse, and that is going to act on a point phi s of P. So this is x1, x2 all the way up to xk, and the result will be the k-tuple y1, y2 all the way up to yk, where psi s composed with phi s inverse is the map phi s of u intersected with v intersected with s, being a subset of r to the k, to psi s of u intersected with v intersected with s, being a subset of r to the k. We number this by 1. Okay, so let me erase this bottom part. Note that since this collection calligraphic U, which is a collection of pairs u comma phi, again we, for notational clarity, we forgot this indices index appearing here, u alpha, phi alpha, right? So since this is a C infinity compatible collection of adapted charts by hypothesis, right? So which means that if I take any two pairs from this collection, they will be C infinity compatible with each other. So since they are C infinity compatible in N, psi composed with phi inverse, okay, so the this is a transition function, and it's a map from a phi of u intersected with v, which is a subset of r to the n, to psi of u intersected with v, which is a subset of r to the n. So this transition function is a map from phi of u intersected with v as a subset of r to the n to psi of u intersected with v as a subset of r to the n. And this is given by psi composed with phi inverse acting on a point of something like this on a point phi of p, which is given by this n tuple x1 x2 all the way up to xk, and the remaining ones are zeros, is equal to y1 y2 all the way up to yk comma 0 0. Okay, so this we number by 2. Okay. And this map is supposed to be a C infinity map, right? Because these two charts are C infinity compatible with each other, is a C infinity map. Now I want you to note that psi s composed with phi s inverse is equal to pi restricted to psi. I'll explain what this pi means in a moment. Pi restricted to psi u intersected with v intersected with s composed with psi composed with phi inverse restricted to phi of u intersected with v intersected with s composed with I restricted to phi s u intersected phi s of u intersected with v intersected with s. Okay, so now I so remember that k is smaller than 1, of course, right? So I is the canonical inclusion of r to the k in 2 r to the n, and this is inclusion, and pi is the canonical projection of r to the n onto r to the k projection. Okay, so now this is a C infinity map. This is a C infinity map. So all the components here on the right hand side are C infinity maps, right? So the left hand side is also a C infinity map. So therefore psi s composed with phi s inverse which is a map from phi s of u intersected with v intersected with s to psi s of u intersected with v. So this map is also C infinity, right? Uh, this map is also C infinity. Hence, we prove that any two charts in this collection u intersected with s comma phi sub s are C infinity compatible, okay, because these maps are C infinity maps. Now, since the union of open sets, the union of open sets in the collection calligraphic U is precisely as okay, is precisely as the open sets in U intersected with S, comma phi sub S also covers S, proving that proving that the collection U intersected with S, comma phi sub S, proving that this collection is C infinity at last on S. Okay. Okay. So QED. All right. So it's a good time to take a break, and we'll be back with the definition of level sets of a map and results concerning level sets of a map in the next segment. Thank you for attending the first segment of the seventh lecture.